Let's take a look at the next example. Let's compute the Laplace transform of e to the negative 3t. The Laplace transform of e to the negative 3t, this is going to be equal to the integral from 0 to infinity of e to the negative st times f of t, which is e to the negative 3t dt. We can simplify this because we have multiplication by like basis. So we can write this as e to the negative st minus 3t dt. And to make this a little bit easier to be in the beginning, or I should say a little bit later, let's actually kind of factor out some of the common factors here. We have a negative we can factor out, and I can also factor a t out, dt. So this is going to be equal to the limit as b approaches infinity of the integral from 0 to b of e to the negative s plus 3t dt. To do this anti-differentiation, we can do a u sub. Let u be the exponent, the negative s plus 3t. Our du then would just be negative s plus 3 dt. So in order to make this integration work, we need a negative s plus 3 quantity dt on the inside. Remember, with respect to t, the s is constant. So we can put that negative s plus 3 on the inside, provided we put a 1 over it on the outside. It's like multiplying by a form of 1. This is e to the negative s plus 3 t dt. This now becomes the limit as b approaches infinity. I'm going to move that negative up to the numerator. We have negative 1 divided by the quantity s plus 3. The integral from t equals to 0 to t equals to b. And now on the inside we have the antiderivative of e to the u du. This is the limit as b approaches infinity of negative 1 divided by s plus 3. The antiderivative of e to the u is e to the u. Evaluate it from t equals to 0 to t equals to b. This is the limit as b approaches infinity of negative 1 divided by s plus 3. U was the negative of s plus 3t from 0 to b. So we get that this is equal to the limit as b approaches infinity. We have a negative 1 over s plus 3 on the outside. And then if we evaluate the antiderivative at b, we get negative s plus 3b minus, when t is 0, this whole exponent for the second term is just going to be e to the 0. So this is the limit as b approaches infinity of negative 1 over s plus 3 e to the negative s plus 3b minus 1. And now let's talk about this limit. So we need to investigate what is the limit as b approaches infinity of e to the negative s plus 3b. For this limit to exist, we need for the exponent of e to be negative. Well, we already have a negative sign here, which means that these two factors, because b is also positive, b is approaching positive infinity, that means that the s plus 3 will also have to be positive. So s plus 3 has to be greater than 0, which means that s is going to have to be greater than negative 3. And then if that's the case, if s is greater than negative 3, then we have a 1 over e to the s plus 3 times b, where s plus 3 is positive, b is positive. Therefore, as b approaches infinity, this exponent will approach infinity, and then e to the infinity, that'll approach infinity itself. And then 1 divided by infinity means that this whole term is going to approach 0. So for s greater than negative 3, the limit of this term, whoops, over here, this limit will approach 0, and thus we get the Laplace transform. This is equal to negative 1 over s plus 3 times 0 minus 1, which is just 1 over s plus 3. So we've successfully found the Laplace transform of e to the negative 3t. The Laplace transform of e to the negative 3t is 1 divided by s plus 3, and again that's provided s is greater than negative 3. Let's go ahead and do another one of these. In example 4, let's find the Laplace transform of the sine of 2t. The Laplace transform of the sine of 2t, this is going to be equal to the integral from 0 to infinity e to the negative st times f of t, which is the sine of 2t dt. This is equal to the limit as b approaches infinity of the integral from 0 to b e to the negative st sine 2t dt. Now, you might recognize doing integrals of this type from calculus 2, but we have an exponential times a trig function. So exponential times sine. We're going to need to use integration by parts here. But not only do we have to use integration by parts, we're going to have to do it 2 times. So let's kind of off to the side, let's kind of work through this part. So in order to do this, let's go ahead and let's let our u be equal to the sine of 2t. Our du then, it's going to be 2 cosine 2t. We will let the dv be e to the negative st, in which case dt, in which case our v is going to be negative 1 over s e to the negative st. So this is going to be equal to the limit as b approaches infinity. Remember, it's u times v. So u times v is going to end up being this. That's going to be a negative 1 over s e to the negative sine, e to the negative st sine 2t evaluated from 0 to b minus the integral of v du. So v and du are these two here. That's going to end up being essentially the following. We're going to have a negative, there's going to be a 2 and an s. We're going to have an e to the negative, I forgot to write my dt there. Sorry. E to the negative st. We're going to have a cosine of 2t dt. We can clean this up a little bit. And I'm not going to worry about this limit quite yet. Let's just kind of hold on to this limit, because this would be the limit of this entire expression. But this is equal to the limit as b approaches infinity of negative 1 over s e to the negative st sine 2t evaluated from 0 to b, plus, this is going to be a 2 over s times the integral from 0 to b e to the negative st cosine 2t dt. Now we have to use integration by parts a second time. Some purists would say you should use variables other than u and v again, but just to kind of keep things streamlined, I'll just do the same kind of idea. Be consistent though, so when you do integration by parts a second time, if I let u be the trig portion above, I'm going to let u be the trig portion of this new integral. So I'm going to let u be the cosine of 2t. As we did before, we're going to let dv be e to the negative st dt. du is going to be a negative sine, negative 2 sine 2t. And then our v is going to be equal to a negative 1 over s e to the negative st dt. So let's work this out. So we have the limit as b approaches infinity of negative 1 over s e to the negative 1 over s sine 2t evaluated from 0 to b, plus this 2 over s times the following. It's again u times v. U times v is going to be a negative 1 over s e to the negative st cosine 2t minus the integral from 0 to b. And that guy should be evaluated from 0 to b. Minus the integral from 0 to b of v du. So it's going to be v du is right here. That's going to be a positive 2 over s e to the negative st sine 2t dt. I'm going to do a couple things to this. I want to kind of go ahead and clean this up by distributing, first of all, this 2 over s, which needs to go to both terms. And furthermore, with this integral, you can factor the 2 over s out because, it's a constant with respect to dt. So we have the limit as b approaches infinity of the following. It's negative 1 over s e to the negative st sine 2t evaluated from 0 to b. This is going to be a minus 2 over s squared e to the negative st cosine 2t evaluated from 0 to b. And then minus, don't forget we have to distribute here. This is going to be a 4s squared. The integral from 0 to b e to the negative st sine 2t dt. And if you're paying close attention, and you might have remembered this is happening from Calc 2, when you do this kind of integration by parts, look at what we have. This integral here, when we take the limit, is the same thing that we started with. That's essentially the Laplace transform of the sine of 2t. So what I'm going to do is let's go ahead and distribute that limit now into this expression. So going back, originally the problem was to find the Laplace transform of the sine of 2t. And right now, if I distribute the limit in, here's what we have. We know it's going to be equal to the limit as b approaches infinity of negative 1 over s e to the negative st sine 2t evaluated from 0 to b minus 2 over s squared e to the negative st cosine of 2t evaluated from 0 to b minus, and now what I'm going to do here is if I call this the integral from 0 to infinity, e to the negative st sine t dt, so instead of writing the limit in front of it, if I replace this and go back to that notation, right, then this thing here, this part is the Laplace transform of the sine of 2t. And so what we're going to do is, right now we have one big old equation. Okay? So if you look at this whole equation here, the ultimate goal was to solve and find the Laplace transform of the sine of 2t. And right now as an equation, here's our equal sign. The equal sign, the equal sign is right here. We have that term on both sides of the equal sign. So what I'm going to do is I'm going to move all of my Laplace transform of s of 2t to one side. And then we're going to be able to solve for it. So just like what you would standard common algebra equation, I'm going to go ahead and I'm going to add 4 over s squared Laplace of the sine of 2t plus 4 over s squared Laplace sine of 2t to both sides. What we get on the on the left hand side is we had the Laplace of the sine of 2t plus 4 over s squared Laplace sine of 2t is equal to, and now let's kind of dive into trying to find these limits. Both of them are the limit as b goes towards infinity. So this is the limit as b goes towards infinity. This is going to be a negative 1 over s e to the negative sb, the sine of 2b, minus a minus will become a plus. We're going to have a 1 over s e to the negative, this will be 0. And then we're going to get the sine of 0. Minus 2 over s squared e to the negative sb cosine 2b, minus and minus will become a plus 2 over s squared e to the 0, and then we're going to get a cosine of 0 there. On this left hand side, because this Laplace of sine of 2t is a common term, I can pull that out. This has a coefficient of 1. So we get 1 plus 4 over s squared times the Laplace transform of the sine of 2t is going to be equal to, again, if it's helpful to think of these limits, what you can do is rewrite this as a 1 over e to the sb, but if s is greater than 0, then the sine term is going to oscillate between negative 1 to 1. The e to the negative s over b, 1 over that's going to go to infinity, and so you can show by the squeeze theorem that this term is going to go to 0. Okay. The sine of 0 is 0, so that's not a limit, but this just is equal to, so I probably shouldn't even put the value notation. This is just straight up equal to 0. For the same reason as this one here, when b goes to infinity, this is going to go to 0. And then we're left with this term here, E to the 0 is 1. The cosine of 0 is 1. And so on the right-hand side, we have simply a 2 over s squared. And now we're essentially done. All we need to do to solve for this is we need to divide both sides by 1 plus 4s squared. Divide both sides by 1 plus 4s squared. This cancels with this, and here's what we end up with. So this is going to be equal to 2 over s squared divided by 1 plus 4 over s squared. And we can simplify this complex fraction simply by multiplying numerator and denominator by s squared. In the numerator, it cancels. So we get 2 all over. When you distribute it into the second parenthesis, we get s squared plus, here the s squareds will cancel, and we get 4. Okay. And again, we said that this was valid when s was greater than 0. Okay. So we've successfully found the Laplace transform of the sine of 2t. It is 2 divided by s squared plus 4, and this is valid for when s is greater than 0. One of the nice things that is coming a little bit later in the section, so you will be expected to do this for a handful of problems on the next unit exam, but very similar to when, if you recall back to when you first had to do derivatives by using the limit definition of a derivative, and likewise when you had to first find a definite integral via limit of Riemann sums. Eventually what we will develop is a table of Laplace transforms, where if you need to find the Laplace transform for specific well-known functions f of t, you won't have to go through this improper integration every single time. You can associate it to a common Laplace transform in a table, and then we'll kind of slowly start to switch to that approach once we do a few more of these.